Hi students, in this video we are going to discuss about the basic signals. Last class we have discussed about the impulse function and we have discussed about the property of the impulse function. In this video we are going to discuss about the unit step function, which is the second signal. Here unit step function, here we can have the unit step function in both continuous time and discrete time. This unit step function will have value only for a time t greater than or equal to 0 and 0 for time t less than or equal to 0. So this is a continuous unit step function. Considered here the discrete type unit step function. This is the this is the mathematical representation for a unit step function, that is u of n is equal to 1 for n greater than or equal to 0 and 0 for n less than 0. Since it is a discrete, we have plotted in a discrete manner and this is what your n. Okay, so this is what the graphical representation and the mathematical relation for a unit steps signal in continuous time and discrete time. Now consider there is a relation that we know impulse function and unit step function now. Okay, now if you are having a unit step function, if you differentiate the unit step function, you will get an impulse function. So let us see how it is possible. Okay, so normally you here from this diagram, the unit step function will have the value from for value 1 for t greater than or equal to 0, right? Okay, so here in a real time the value will directly will not attain the value 1, so it will take some time to attain the value 1. Okay, so this is the delay. Okay, so here this is what the practically you will get a unit step function. Okay, so it will take some time to attain the unit step function, which was some duration, some delay you will get it. Okay, so now this is what your unit step function. Now when you differentiate the unit step function, you know, when you differentiate a constant, what you will get a 0. Yes, when you differentiate constant, this is the constant value, right? When you differentiate the constant, you will get a 0. So this is what a slope, which is nothing but t, something like that. Okay, so here is a constant variation. When you have a constant variation, when you differentiate t, what you will get 1, right? So that is when you differentiate x, what you will get 1, right? So that is what the constant you are getting. Okay, so which is nothing but a unit impulse function, which is a unit impulse function. So if we have a unit step function, if you differentiate the unit step function, you can obtain a that is an impulse function. Next one is a signum function. Next is the signum function. In this signum function, you are having continuous time as well as the discrete time. So this signum function will have a value 1 for time t greater than 0 and minus 1 for t less than 0. So I have drawn like this. For time t greater than 0, it is 1. For time t less than 0, it is minus 1. This is the discrete case. Here, if you consider this origin value, right? So when you consider in case of continuous time, actually here it is 1, here it is minus 1, so it is 0 at the origin. So because it is continuous, we may not able to specifically write for a 0 value. For t greater than 0, t greater than 0 implies the 0 point not 1, from that itself it is 1, right? So here it will be like this. Okay, from here it is minus 0.0001, like that. Here you can have the value minus 1. So here signum of t can be represented in like this. Okay, so secondly, here consider a discrete time signals, because discrete time signal will have value only at discrete time instance. Okay, so here we are going to represent this signum function. For n greater than 0, it is 1. For n less than 0, it is minus 1. At n is equal to 0, it is 0. So this is the mathematical relation for the signum function. So a discrete time signum function. So this is what your continuous time and this is what your discrete time function. So the next function is a ramp function. In the ramp signal, what is the mathematical relation is r of t is equal to t for t greater than 0 and 0 for t less than 0. Now consider the value of t when t is equal to 0. Here r of t is 0. When t equal to 1, r of t contains the t value alone, so r of t it is 1. When t equal to 2, here it is r of t equal to 2. When t is equal to 3, r of t equal to 3. Okay, so when you join these points, you will get a function like this, that is a ramp function. Okay, this is what increasing like this. Okay, this is what a ramp function. Now consider a discrete case. So at n is equal to 0, it is 0. Okay, at n is equal to 1, it is 1. At n is equal to 2, it is 2. Why it is n is equal to 2 here? Because whatever n value we are taking, it is equivalent to, we have to assign that for r of n. So here you will have a ramp function like this. Okay, now here also there is a relation with related to unit step function. What is it is, this r of t is, we can represent this as t into u of t. We know that u of t is a unit step function, right? This is what your unit step function. When you multiply this function with this function, what you will get? You will get the ramp alone, right? So this is nothing but the expression for t. Okay, t into u of t. This is t, which is actually this is what this is equivalent to t. So when you multiply r of t with, which is equal to t into u of t. So here how will you obtain a ramp function? Just by integrating the unit step function. So when you integrate the unit step function, you will get a utd of t, you will get a ramp function. So otherwise you can say as, if you are having a r of t, okay, so if you are having a r of t, when you differentiate this, so if you are having r of t, when you differentiate this, you will get a unit step function. Okay, so consider this is a variation, right? T. Okay, so now see here, when you differentiate t, what you will get? You will get 1, which is nothing but a unit step function. Okay, so when you differentiate r of t, you will get u of t. When you integrate u of t, you will get r of t. Okay, so this is what vice versa. Okay, so one signal can be obtained from the another signal. Next one is a continuous time triangular function and discrete time triangular function. So triangular function you can generate in any manner. Okay, here I am going to generate only one cycle. So here I have chosen -1 to 1. Here also you can choose 0 to 1 and you can have a triangular wave. So here I have chosen -1 to 1. Okay, and 1 minus mod t. When I choose -1, when I substitute -1, so -1 it will become +1. So 1 minus 1 will become 0. At -1 it is 0. At t equal to 0 it is 1. So here at t equal to 0 it is 1. At t equal to 1, 1 minus 1 is 0. So it is 0 here. So when I join like this, so these 3 points I am getting a triangular wave. Okay, so if you want to check at in between points, if I substitute -0.5 here, mod, so it is +0.5. So 1 minus 0.5 is 0.5. So I am getting here 0.5. Similarly, when I substitute 0.5 plus 0.5, it is same similar. So 1 minus +0.5. So you will get the 0.5 value. Okay, so the next one is a discrete sequence. The same, instead of t, I am having n. Similarly, I have substituted the different values of n, that is -1. So 1 minus 1 is 1. So it minus 0.5. So it will become +0.5. So 1 minus 0.5 is 0.5. Then at 0, it is 1. Then at 0.5, 1 minus 0.5, it is 0.5. Then at 1, it is 0. So here it is a discrete time triangular function. Okay. Okay, the next function is a sinc function. Here this is the mathematical expression for the sinc function. Sinc function is equal to sine pi t by t. So this extends from minus infinity to infinity. Okay, now we will substitute different values. First substitute n is equal to 1. In this case, when you substitute t is equal to 1, so it will become sine pi. So sine pi is 0. So here you will have 0. Similarly, you will substitute 2, you will get sine 2 pi, which is also 0. So like that you will get it. So in between point, just t equal to 1.5, you just substitute here and find out the value. It is just a representation, no need to mark down the values. And now consider a time t equal to 0. Okay, when you substitute t equal to 0, in this case what happened at the denominator, when you substitute t is equal to 0, the term will become infinity, so which is indeterminate. Okay, indeterminate. So it is not possible to have infinity at this point. So what we need to do is, for this case, we need to apply L'Hospital rule. What's L'Hospital rule is, so you will have a sinc function, right? So here we need to differentiate the numerator and denominator separately with respect to that function t. Okay, so now consider sine. It is, when you differentiate, it is cos pi t into pi divided by, when you differentiate t, it will become 1, right? Cos pi t by, 1 second, sorry, here it is, I have left off pi, so sine pi t by pi t. Okay, so this is what your sinc function. Okay, sine pi t by pi t. So I will explain again. So first substitute t equal to 0. So when you substitute t equal to 0, in this case what happen is, it will become infinity, so it is indeterminate. So we are going to apply L'Hospital rule. So here what you need to do is, you need to differentiate the numerator and denominator separately. So when you differentiate the numerator, it is pi cos pi t divided by pi. So now substitute sinc of 0. So when you substitute sinc of 0, cos 0 is 1. So pi by pi is equal to 1. So only you are getting here the value, maximum value is 1. Okay, so now when you substitute t equal to, when you substitute t equal to 1, so what will happen when you substitute t equal to 1? It is sine pi by pi. Sine pi is 0, so automatically you will get 0 at this point. Similarly, you have to substitute different values of t and you will get a sinc function. Okay, so similarly you can obtain for a discrete case. So you will have samples only at this particular time instance, like this. Okay, so in real time, normally we will deal only with the continuous time sinc function. Okay, so here this is what the about the characteristics of the sinc function. Next one is a rectangular function. So here the rectangular function, here this is what a rectangular function is. So here this is the mathematical expression, x of t is equal to 1, which is equivalent to minus, that is for the range minus a to a. So minus a to a, the rectangular function take the values of 1. And similarly for discrete case, it is the range minus n to n, the value is 1. Okay, so this is what the rectangular function. Similar to your sine waveform, you cos waveform, you know the expression, right? A sin omega t, a cos omega t. So similarly here, these are all the basic signals we will use in our use as a input to the system. So you need to know this mathematical representation and its graphical representations. That's why we are studying these basic signals. Next, finally, is for exponential signal. This is what the expression for exponential signal, that is x of t is equal to e power alpha t. Okay, here alpha, if it is greater than, no, it is an increasing one. If alpha less than 0, it is a decreasing one. So this is what about the basic signals.